right. Here comes the glorious Zoom. Looks like things are working. Good, I'm on the guest network. The staff network hasn't worked in days. And I will try muting these guys. As more people join, you'll probably have to remind me to mute you several more times. You know, there's supposedly Zoom settings somewhere to make it just mute everybody. And I thought I had that turned on. Maybe I'm gonna, we got a couple of minutes here. Let me see if I can figure out how to do that. Meeting settings. Join before host. Mute automatically. Neat. I thought that was on, but it doesn't seem to be on. Maybe that will do it. I wonder if I have to hit save somewhere. We'll see. Maybe I found the button. All right, anyway. So we are here. Oh, let me turn off this ghostery. It will just be depressing to see everybody spying on me. All right. And turn back on the ad blocker, if I can find it. There it is. Okay, good. All right, so we're here at 127. And we're on February 10. Okay. So, scheduling stuff to put up here. Good, a pen. So today, chapter 4 quiz, project 0, 1, or 2 do, okay. Okay, next week, no class. After that, chapter 5, project 3 and 4, good, okay. Good. Are there any questions about anything? I know a couple of people had questions about projects before class, but maybe those have been addressed. Let me just, I want to wait till 10 after to do the official stuff here so people have time to show up. I'm going to get this ready to go.
So are the projects due at the end of the day or?
At midnight. Yeah. I make the quiz due before class, but the projects due not till midnight. Good. And I'll take them late, but you only lose.
But the double asterisk ones, you said they won't be late until February the 10th, you mean midnight?
Yeah. Well, the projects, yeah. The quizzes before class. They're late after that.
But I mean the old quiz.
The old quiz is the same thing. Yeah. But you only lose 2 points for being late on quizzes and 5 points for being late on projects. Aha, a question. The quizzes, please keep them available until, oh, they're available forever, but they are late after class. There's only 2 points off for being late, however. But I'm going to leave them available until the May something, so you can take them late. Good? All right. And let's see if anything else is worth talking about. We talked about some news earlier. Let's see if anything else fun is happening. This one, I didn't actually get to this. That's a pretty cool article. And not quite sure what to make of that one. This one's kind of interesting. So this, anyway, here's all the details of North Korea hacker army. This is quite a scoop. They got a, there are 2 people I read about recently from North Korea. There's a woman in North Korea who blew up an airplane for the North Korean government and then escaped to South Korea. And instead of imprisoning her, they sort of let her reform, and now she's free. And she talks about how she was just totally brainwashed in North Korea and is sorry that she did it and stuff. And there's another, this guy was one of their cyber spies, came south, and he talks about, it reminds me of the Moonies. I know when I was a kid, they had the Moonies in this cult group selling flowers, and each one of them had to make a lot of money every day, and they weren't allowed to go home or anything until they made enough money each day. And North Korea is apparently the same. Each hacker has to make $100,000 a year. And if they don't, they will be punished and sent off to like concentration camps or something horrible. And so that's why they send out all this spam and ransomware and crypto locker and everything. Most of that stuff comes from North Korea. Like WannaCry. And this guy talks about his life doing that. Everybody required to earn $100,000 a year, any means possible. And that's why I've heard North Korea, their army is not very talented. As we said, they're not like super hackers or anything. They're just under enormous pressure, and they're just using elementary techniques to do this. No one ever accuses them of being terribly technically sophisticated, but they're very energetic. Yeah, I mean, even very simple attacks will get you money. Like we were talking in the last class about social engineering. Just old-fashioned cons that have worked for centuries still work. Trick somebody into giving you their money. So this guy bypassed on Linux ASLR and non-executable stack. It's kind of cute, and we'll be using some of these techniques, but it's kind of good to see. He uses a few slightly different tools, but mostly it's just GDB. Use objump and GDB. And both of these techniques, he used return-oriented programming to get past both of them. So instead of injecting code, he uses code that's already there. And we'll be doing that on Windows anyway. I don't think I have a Linux project, but this is one you could do, where you make your attack. Instead of injecting an exploit you get from like MSF payload, you piece it together with pieces of the code that's already there, like making a message by cutting words out of the newspaper. And there are automated tools that will do that. On Windows, it's Mona we will use. Mona is the tool that will construct an exploit out of existing code. And that way you do not need to inject any code. All you inject is a bunch of addresses. Go to this address, this address, this address in the stack. And you do not have any active code in anything you injected. And that defeats address space layout randomization and data execution prevention, because you are not. The address space layout randomization means you don't know where things are and you're using code wherever it is. And the data execution prevention means the stack is not executable. So you cannot put in a string and then execute it, and you're not doing that. You're using code in another section that is in fact executable. So it's pretty powerful. And we will be doing that on Windows anyway, not so much on Linux, but if you want to, I put the link at the bottom of this page for a couple projects if you want to. Do this. Here's a couple of Linux bypasses of those. We're going to be dodging them today. So it's 1:08. I think it's close enough to the time to start. So today it's format strings, and we're just continuing the general story here remains the same. The problem is that C is stupid, and this is by design. C is supposed to be small and fast. So C never wastes any cycles trying to argue with you about what you're doing. If you tell it to do something, it just does it in the most efficient way possible. And all other concerns of security and double checking is your responsibility as the coder. The language will not attempt to prevent what you're doing. So this means you have a weird situation. So first, the fundamental issue I mentioned before that all hacking pretty much relies on is that your computer does not know what it's doing, and it doesn't know what the data is. It's just a bunch of ones and zeros. It could be a movie or text or executable code or high-level instructions, and it would all look exactly the same to the computer. So almost all these attacks involve tricking it into thinking something is text under one circumstance and then being reinterpreted under another circumstance as active code or something else. So this affects you when you use C in a very simple way. You can print out data, and the same data can be printed many different ways. You might call it you might interpret it as a decimal number with a %D tag, or a hexadecimal number with %X, or an ASCII character with C, or a string with S, or a pointer with P. And all of those are perfectly valid ways to print something. So you have to tell it how to interpret the data. And therefore, the printf command in C, and all other languages have this too, there is a format string where you tell it how to interpret it, and then there's a variable list like I, J, and K. So print out I, and when you print it as a decimal number. But when you're printing out a word down here, these strings, interpret that as an S, a string. So print out a word instead of trying to print some kind of numerical value. Yeah.
Percentage?
Yeah.
Okay.
Yeah, and that's percentage is what you often use in C. Percentage, you have to use it in C, and other languages often use it too. So they just have a series of format specifiers like %D and %X. And so I'm not going to bother doing this one live, but there's the point. I, J, and K can be printed out as decimal or printed out as 5-digit decimals with spaces leading them. Or you can print the same thing out as hex values, 1, F, and 1E, instead of 1, 15, and 30. It's the same binary data. The only difference is in how it is presented to the user. The computer doesn't know the difference. And so you can print them out as individual characters or as hex of numbers. Here's strings, here's pointers. So you can print a string variable as a string, and that means it will go to that address and look for a series of bytes and consider it a string until it hits a 0 for a null terminator. And that's how it gets hello. But if you print it as a pointer, it will print the address of the string, of the first byte, which is completely different. As far as C is concerned, they're both the same object, but you're using them differently. So the one that really gets us, though, is %x. %x prints out values hexadecimal. Usually they're 8 bytes long, but if it's a small value, it might delete some of the leading zeros to be different lengths. You can specify the length with %8x, then it will always be 8 bytes long, or you can make it longer, 10 or 100 bytes long. Okay, which we're going to do. And the other one, which really matters, is %n, which is insane. I have no idea why it exists, but that's what we're going to use. So here, the fundamental issue here is that C, suppose I call a character, I define a character named 10. What this does is it makes a variable called name. It gives it a pointer pointing to an address on the stack, and then it reserves 10 bytes of space on the stack to store data. Then I call stir copy to put more than 10 bytes into there. Now the stir copy routine does not bother to look at the previous assignment statement. What it does is the simplest thing it can do. It takes the pointer to name and pushes it on the stack. It takes the pointer to the Rumpelstiltskin and pushes it on the stack. I think it goes in the other order. Then it jumps to this stir copy function, which looks on the stack. And it takes the first thing it finds on the stack and puts it in on top of the second thing on the stack without checking the length. That's what it does. So the fact that I did not prepare the data correctly is not known by stir copy. It just does it, assuming you have the stack ready to go. And if you don't, it has no way to tell because it's outside the whole point of C for it to try to somehow guess what you mean and decide you don't mean what you said. The whole job is to just efficiently do what it says. And this, you're encouraged in C to think of brilliant creative solutions. So every function is supposed to do exactly this one function, and you're supposed to think of some clever way of making the pointer point somewhere strange and making it more efficient. So it would never double, it will assume you have some plan. And that means you can do this. You can print a string without any arguments. You can have a format string and nothing to print. Now, if this was a language like Visual Basic or something, you would complain, say, you can't do that. You can't have a format string. It has to be followed by like I, J, and K, something to print. But the program can do it. It will just push this onto the stack, call the function. The function will just print using the format string as the first thing on the stack, and then assuming that whatever follows it on the stack must be whatever you're printing. Because it doesn't know that you didn't actually prepare the stack. The stack is just sitting there, so it just uses it. So you can now read stuff that was not intended to be read by the programmer. So we'll make this program. Let's get this stuff live. I've got, by the way, there's a new version of Kali I saw, so I went and got that. It seems to be, for our purposes, the same as 2017.3, but they often foul things up, so I wanted to not make any assumptions. Okay, we're going to need 2 of these. All right, SSH. Wonder if I have one. Nope, I don't. Okay, SSH 172, 16.1.250, I think, is my new machine. It is, okay. All right, so I now have a couple of SSH sections. If I can figure out, oops, I need to do root at there. I'm getting there, root at my IP address, and then my high security password. Okay, now let's go into 127. In both of these, we're going to need 2, of course, because I'm going to later on want one of them to be the debugger and the other to be the attacker. They're both just SSH sections. So if I look, I have some various programs here. The main program we're going to attack is fs.c. So let's look at it. This is the simplest program I could make to do this. I had to modify it a little bit, but all this program does is include a few libraries, then define a 1024 buffer, then copy whatever comes in the argument into the buffer, and then print the buffer with no format string. and then print in. Now this is allowed if you print something without a format string. C will use some arbitrary chosen format for it, like hex or something, and it's something you might do to debug something. I'm not going to bother to make it pretty. I'll just print the value. But what you can do is I can put in that string a format string. And then this command, which the programmer might have intended to print out a value without bothering to format it, can print out a format without any value to print. So let's look at this. If I run this thing, and by the way, to compile it, all you need is, for what we're doing today, I use this compile, no position independent executable. So it will not put everything in page 0, where all the addresses start with 0. And then the other thing I did was turn off the stack protector, which I forgot to put in my slides, but it is in the project. This is all following a project. I think it's project 5, project 6. So when you compile it, I would also do this -z exec stack. If you don't do that, then later on we'll have a problem. You won't be able to execute your code. So in fact, let me just put that in my slides here, and I'll try to remember to update them later. Let's put in text of that. There we go. Get rid of this, pardon me. There. That is the right way to compile it. All right, I'm gonna save that. That's the way to do it. So now let's do that. GCC. Okay, so I save this, I compile it that way. Now I have this thing. Let me make it higher on the screen and bigger. All right, and bigger. Okay, now I have this thing called FS, which is executable, and it's only 7,000 bytes big, and I can run it. If I run FS and I put in hello, it prints hello, because all it does is take whatever I put here and then print it in a printf statement where it's the only thing printed. And that's fine if I'm printing normal text. If I was to print a number, it would print some version of that number. All right, so it just prints something without formatting. The crazy thing is when I start putting in a format string here. So let's put in %x. Now it prints a strange value in hexadecimal because it interpreted this as the format string and it just printed the next thing on the stack, which it assumes is my variable of choice because the printf routine does not know that the main routine did not set up the stack correctly. It just uses whatever stack it finds and executes it. So you can now put a bunch of that up there, and let me go back to my slides. Yeah, I don't even need the quotes. All right, so you can do this. You can put a bunch of %x's. There's 4 of them. Now I get 4 bytes worth of stuff in hex. If I want it to be easier to read, I can put it in a delimiter. I can put something like a dot here. Now a space would probably foul it up because it would interpret it as a different argument. Yeah. It is in, it's ESP minus a number going down into the stack. Yeah, ESP is the first one, and then the next one and next one as it goes down. And we'll see them. It's a very good question. It's starting at ESP and going down, not EBP. EBP is the bottom of the stack. It'll start at the top of the stack because what you do is you push onto the stack the arguments and then you call the function. So it expects them to be right on top at ESP. Good. So it pops them off. So this now gives me the next 4 bytes on the stack. So that's kind of crazy. Now let's play a few more games. So this one, now I have an information disclosure vulnerability. I can now see things that I was not supposed to see. So I could put hundreds of %x's and I could be viewing the contents of memory that's none of my business. The most obvious consequence is I certainly could overcome address space layout randomization now because I can find exact addresses for things like variables. So I'll find out where they are. I might even find something good there like passwords or something if I'm lucky. So that's the first kind of vulnerability. But here's the next one. You can use the %n. %n is crazy and this causes a seg fault. %n, I have no idea why it exists, but what %n does, %x will take the value that you're printing and print it in hexadecimal. %n will take the value and interpret it as an address and write to that address. And the number it will write is the number of bytes that have been printed so far in the print statement. I don't know what the point of this was, but I can now, this is an arbitrary read. I can now read from memory. This is a write. I can write to memory. And this way I did it with %x, 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 %n, it will take the fourth word on the stack as an address and write to that address. So now, here's another thing. The value I'm putting in goes on the stack as a temporary variable. So I'm controlling some of the stack. This %x stuff I'm putting in is also on the stack. So if I put some text first, like this, if I put in some capital A's, and then let's just have %x all the way, this is what I get. The first byte is here, the second byte is there, the third byte is there, and the fourth byte should look familiar. The fourth byte on the stack is the A's I put in. This string I put in is also on the stack somewhere. So I control some of this. And here come some questions, which is appropriate because this is the heart of it. Okay, syscontrol random stuff, okay. Someone's posting a lot of stuff about ASLR. Oh, would each successive run point to different values with ASLR? And it would. That's quite correct. So I think that's correct. With address space layout randomization, I should be able to see variation in these numbers. And here's somebody doing it and getting different numbers. He ran it several times, and you see he got different values. BBEC 6653, yeah. So with address space layout randomization turned on, these things will move. So now we're getting very close to having control of the machine. Now we can do an arbitrary write, and we can control what we're writing to, because these bytes go there. And you can prove it, because if I go to, say, BBBB, then I get 42s here. So now, here's the logic. The first 4 bytes I put in become the fourth word on the stack for this program. These 3 are just fillers. I can now put a %n here, and it will write to that address. So now I can target any memory address and change it. There's one problem is the thing I'm putting in there is kind of stupid. It's equal to the number of characters printed so far. So it's going to be some stupid number like 10 or 20. But we'll cross that bridge when we get there. And that is why I got a seg fault here. When I print with the %n, it's changing some memory somewhere, wherever it points to, and it turned out that this pointed to some memory I'm not allowed to go to, which was the hexadecimal version of the first 4 bytes here, %x and such. And here, it's going to crash too if I give it FSAAA, %n, %x rather, %x, 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 %n. This is going to take AAAA and then try to write to it. And it will crash, of course, because AAA is not an available memory address to my program. My program has a memory region near 0804 where there's code, and it has another region way at the top in FFFF for the stack, but AAA is not an option. It's not available to it. So I now have, notice what I did. First I found information disclosure, then I found something that crashed it, like you might with a fuzzer. Now our goal is to do more than crash it, to take over the machine by carefully controlling the exploit there. So that's the game, and now we can do it. By the way, this works for all of these functions, printf, fprintf, sprintf. There's a whole bunch of C functions that work the same way, and they all have this vulnerability. So you can prevent this, by the way, but not very easily. Stack defenses won't do any good because we are not overrunning the stack. We're not replacing the stored extended instruction pointer or anything. So a canary at the end of the stack will not stop this because we're not filling memory to hit the location. We're targeting it directly by address. Address space layout randomization and a non-executable stack will make it more difficult. At some point, I'm going to try to inject shellcode and run it, and they would make it more difficult to run the injected shellcode. So they would help somewhat. Static code analysis tools are actually good at finding this. As you can imagine, all you need to do is scan the source code and look for a print statement that doesn't have a format string and a variable in it. That's a simple syntax. You could even do it with grep. So it's very easy to prevent this if you run some kind of syntax checker on your C code before compiling it. But if people don't, you're hosed. GCC will sometimes warn you, but as you saw, this modern version of GCC didn't even complain about this. So now we just need to take over the box. So here's the game. I now know I can control a parameter and I can write to an arbitrary memory location. So now the question is, how do I take over the box with an arbitrary write? What I need to do is I need to inject shellcode somewhere, find out where it is, and then write to some address that will eventually turn into the EIP. And there are various ways to do it. Now, one thing I could do is I could write to the stored EIP at the end of a stack frame. And then when I return, it would hit it just like we did before with a buffer overflow. That could in principle work, but it turns out that there are easier things to shoot for. But here's some things. You could target a saved return address, and when that function returns, it'll run your shellcode. But what's more fun is to hit the global offset table, which is what we're going to do. But there are other things. When you launch a program, there are constructors that create some data structures you need. And when it ends, there are destructors that clean up those routines. And you could target the destructors table. So when the program is over, it runs your shellcode instead of cleaning up after itself. You could also overwrite any of the C library hooks. And then when it tries to actually use a C library routine, it'll run your shellcode instead. There's a thing it runs when a program ends called @exit. If you target that, it'll be like the destructor. It's something that's run automatically when the program stops. Any function pointer will do. And in Windows, there's a handy thing called the unhandled exception pointer. We'll be using that later when we get to Windows, especially in earlier versions of Windows before Vista. That was always at an easy to find location. So it was a handy place to take over a machine. If you could write there, you could very easily take over the machine. Microsoft has made it a little harder to find, but that's still a working technique. Yeah.
If you entered %x 4 times and then you do that and cycle it around, like, is that arbitrary or is that?
That is arbitrary. It's a question of how the code is written. In your textbook, there's an example of a real commercial software, or I think open source. And in fact, they found that if you type in AAA, it only affects the 300th word on the stack. So you have to have a long mess. All you know is that the data I put in is on the stack somewhere. You could have to hunt for it, and it could take a while.
What's the technique for doing that?
What you do is you can use a $ number in the format string to skip over a bunch of fields. So I mean, you could just make something that prints out like 300 X's, but you can also make something that prints out like 10 X's and then skips 10 and prints 10 and skips 10 and prints 10. And that technique's in the book. So not in this lecture, but it's not that hard. But it is. I thought it was unnecessary at this point. But yeah, that's how you do it if you're further down the stack. We have a very simple program, so there's not very many variables, so it's not very far down the stack. That's a good point. Will I be showing autofuzzers? I'm not planning to, but if you have good ideas for autofuzzers, send them to me. My fuzzing, I have trouble finding a fuzzer that's easy to use and still effective. So you'll see a couple of fuzzing projects towards the end, but if you have good ideas, email them to me or put them in the chat, because I could have a better fuzzing project, and that would be a stronger thing to add to the course. So please give me tips to make the course better. I'm always interested in that. So now let's look at how this program works. So we're going to do what we always do. We're going to look at it in GDB. So I'm going to run it in quiet mode so it doesn't print a bunch of garbage at the start. So now I'm running this in FS. There's my code. I can disassemble main. This doesn't have a subroutine or anything. It just has main. And remember, the way you use GDB, if you don't want to read assemblers, you just look at the name. Here's string copy. Remember the code. In fact, let's go back and look at our source code here, which was right there. There's my source code. So let me zoom in a bit here. If I figure out how to zoom in. Shift thing. There, good. All right. So there's my source code. And here's my object code. So it prepares some stuff. It's missing an include there, but it doesn't matter. Then it does a string copy, a print, and an exit. So here's the string copy. Here's the print. Here's the put character, which is that print. And then there's an exit down there. There. So like I say, just read the functions. There's the string copy. The string copy just prepares one thing on the buffer. This is where the actual error occurs, printf. It does the printf without a format string, which is what I trick into doing something unexpected. Later on, it's going to call putchar, and then it's going to call exit. So if I can just overwrite the pointer to putchar or exit, that would be an easy way to take over the box. because it'll be running normally up to this point. At this point, I will abuse this print statement to change one of these pointers. And now when it tries to call these library routines, it'll call my shellcode. That's the plan. Okay, so let me shrink this down to normal. And there, I can do it right here. And, okay, so we talked about that. We're controlling a parameter. Okay, so now let's get the global offset table. You can do that from here with objdump. We've used this before, objdump. If you do -D, it will disassemble the whole program, but we've already done that. If you use -R, it gives you the relocation table of FS. And this is the dynamic relocation table. Because we did not use -static when compiling, it did not include the libraries in the code. That's why it was only 7 kilobytes big. That was intentional. I want to use shared libraries for this attack because the way you use shared libraries is it has a relocation table which goes and finds the library that's already loaded in RAM from some previous program, the same way DILs work in Windows. And that means I have a handy place to take over the box. This is the dynamic relocation table. And I'll come back to that, but first let me show you another fun command in GDB. GDB is here. I learned this recently. You can do info files. And this gives you the memory map in a very nice way. I'm going to make this window taller and just do that again. There. This is good, clean fun. These show me all the sections of the file. We've talked about this before. The text section is where the executable code is. The data section is where a lot of data is. This is the global object table. And this is the programmable link table, GOT and PLT. This section here is the one. Notice that it is not very big. 0804 A000, 0804 A020. This is only 32 bytes big. That is the table for that's the global offset table for dynamic relocation. These 32 bytes are that. That is the whole thing for this simple program. All it uses is a few routines, like printf, string copy, exit, and put char. Now, you could overwrite any of these with this attack. When I originally did it with an earlier version of Kali, I attacked put char, but here's a subtlety. You can't do the last one. You have to do one in the middle. And you'll see why, but it turns out that in order to write 4 bytes, I have to write 3 bytes past it. And if I try to rewrite the last one, some of my write operations will go out of this segment and cause a segmentation fault. So just like you can't go past a 0 when injecting a string, you can't use a format string to change the last item in the GOT table. So what I did was I added to the source code the exit command, which wasn't there before, just so I would have 2 function calls after the print, and one of them would be up here. And it turns out in the latest C compiler included in Kali, it puts the exit here before the end. And the order in which these things go depend on your compiler optimization and everything, so it's kind of random. So, but you do need to find something to overwrite that you can find and that is not right at the end of the segment. So this is it, 0804 A014 exit. So if I can write to that location, I can take over the box. So that's the game. So I want to write to the GOT. And this is going to be easy. Remember, it is the input string I put in that controls that address. So the active ingredient is this run command right here. So let me just do this. If I go here, I'm in GDB. Now I'm going to put a break. Let me just go through the steps. So I disassemble main. I will see the printf is here. So I want to look at the condition of the machine after that printf. I could break anywhere, and my plan is I'm going to hijack this exit. So anywhere in this region is fine to put my breakpoint. This is after the attack has changed a value, but before I jump to that value. So I'll just choose the next command there, which is main plus 76. So I'll put a break there, main plus 76. Okay, now I want to watch this value here. I'm going to do x, 1x at that address, 0x0804. Let me make this a little bigger and a little higher. All right, 0804 A014. That is the pointer to exit. And right now it contains the real address of exit, which is 0804 or something. That is the real path that will eventually lead to exit. I'm going to change that. And so now the way I change it is by just running this mesh. So let me copy it and put it here and then talk about it. Okay, what this does, this is going to feed in, remember what I did with the A's. It's going to feed in 4 bytes, 14A00408. And this is the way you hexadecimally refer to bytes. We've seen this before. That is going to change the 4th byte on the stack. 4th word on the stack is going to turn to this address backwards. This is going to print the next 3 words on the stack. This is going to print to that address. So that is going to change this value when I run that. Now, if I do an examine of that, it has now changed from the original value of 8048366 to 0001B, because that is the number of bytes I have printed, which is a small number like 25 or 30, 1B. So I have now destroyed this pointer. I have written junk on it. So this is proof of concept. I'm not going to be able to take over the box. If I continue, of course, it's going to segfault because that address is not a valid address in the text section. It doesn't have any, it's not allowed to use that. So I've still just now gone to a DOS. This makes as much sense as putting AAA on there, but I now have successfully targeted this value and it is used for the jump at the end of the program. So all I have to do is more carefully control the damage I do to that, and I can win. So here, let's put it in Python like we always do. Make this big, and this is file F1, so I can just look at it here. If I do nano f1.py, okay, here's my program that will write 4 bytes on the stack. So the first thing, I printed 4 words here. Now, let me make a simpler one here, just for starters. I'm going to copy that to f0.py and do just 1 word for starters. There. So let's make this simpler, just have 1. And let's XXXN, get rid of all this, just to go in small steps. Okay. So this is the attack that does just what I just did. It's going to write those 4 bytes to target this value, and then have just 4 bytes of junk here, it doesn't matter. Print out 4 things here and print %n. That's going to change it. So that should do it. And I saw a chat message. Let's see. Could you elaborate on why %n writes on the stack? Yes. I wish I knew why. I can tell, but it is a fact that %x prints the value of the current variable in hexadecimal, and %n takes that value, interprets it as an address, and writes to that point. I have no idea what legitimate purpose there is for this activity. It sounds insanely dangerous to me. But that is just the way C works. There is this %n format, and that writes to memory specified by a variable. Obviously, that could be useful, but ridiculously dangerous. Anyway, so F0 should do it. So if I run that one, I can run and get my run f0.py. That will feed in the data from that. And if I restart it from the beginning, it goes here. And now if I examine that, it put the 1F in there. So this one put 1B in there. Now I'm getting a 1F out of my program. So this program, this F0 program, writes 1 byte of data onto the pointer. Yeah. Yeah, I think that's why this extra 4 bytes here is why the number is a little different. Yeah. All right, so now let's try the next one, which is F1. So now how do I write a whole word? I need to write a whole address. The way you do it is you write 4 times. You're always writing 32 bits. So the first time I write these 32 bits. The next time I write those 32 bits. The next time I write 32 bits over here. Let me just draw this someplace where it's more visible. So I have bytes like this one, and then this one. Okay, there's 3 bytes. So I'm going to write into it. And let me put A's in where I write. So what I do is I want to target the 1s. So first I write this. And then the next time, I write, okay, we're getting there. Next time I move over one and do this. And let's not worry about little endingness right now. Let's pretend they're just in order to make it simpler. So there. So I write a word here. Then I move over 1 byte and write a word here. That's how I change this value. Then I move over and write a word here. Then I move over and write a word here. There. So with 4 writes, targeting a target that is 1 byte off every time, I can gradually construct anything I want, and I have 3 bytes of collateral damage. The next pointer over is going to get all trashed. This is something we've seen before. I have control of something, but I have collateral damage. So remember, I have this table of various pointers. I'm going to change one pointer and mess up another. That's the plan. That's why I need 4 writes to do it. So here's the code that writes all 4 bytes. This writes to byte 14, 15, 16, and 17. So the byte 14 is going to get written once. Byte 15 is going to get written twice, first by this one and then by that one. Byte 16 is going to get written 3 times, but the last write is the only thing that matters. So I can change all 4 of those bytes. That's what's happening here. So %n is nothing printed. The corresponding argument must be a pointer. The number of characters written is stored in the, that's right. That's what happens. He's trying this, I think, on a C manual. Number of characters, that's what the C manual says. The number of characters written so far is stored into the pointed location. That's what we're using. It sounds like it was written just for us. So this will now write, and that's why this has to have %x, %n, %x, it has 4 %n's in it. And it has this junk in the middle for some reason I've forgotten, but I'm not going to worry about it. This will now write 4 times. So let's run this, and that goes here. I can just run $f1.py and start it from the beginning. And now I get 37, 30f, 47, 40f, which if you know your hex, it's 8 bigger every time, because each one of these writes prints out an 8-byte pointer. So the number of bytes written is larger each time by 8. So now I can write 4 bytes of junk. Now I just need to control it instead of it being numbers like 37 and 4f. And for that, all I have to do is this. If I want to hit A, B, B, C, C, D, D, I calculate it this way. I subtract a number here, which is this minus 8, which is 2f, subtract it from each one. And now, for each one, I have to add 256 because I don't want to have any negative numbers. And remember, I can be 256 is equal to 0 for our point of view because we're only caring about the last 8 bits. So I can add 256 as many times as I want and it won't matter. So this will take 256 minus 2f plus b1, and anything I put in b1 will now get written there. The next one has to do the same trick, except I need another 256 to make sure it's never negative, and I need to subtract n1 because however many bytes I printed this time are now included in the total. So that's the pattern. Now I have to subtract n1 and n2 from here, and n1 and n2 and n3 from here, and since I'm subtracting a bunch of things that might go up to 255, I have to keep increasing the multiple of 256 to make sure it's never negative. And this is just the way to make sure that I get the desired single byte here and here and here. So if I've done it right, this will write A, B, B, C, C, D, D. And that's it. So let's see if it works. That's this one, F2. And when I did it, it didn't quite work for me. I got A, B, B, C, C, D, D, E. It was off by 1. Now, if you were into theory, you could probably figure out why it's off by 1, but I gave that up long ago. All of these attacks are often off by a little bit, and I just accept trial and error. When I'm close enough, I say, well, obviously, I'm off by 1, so just take the 1 out. Now I put a -1, -1, -1, -1. And I didn't really worry about why. You guys are welcome for extra credit to figure out why. But I just wanted to get it to work. because don't pretend to be that smart, and they keep changing everything anyway. So I'm accustomed to, once I get some control of the machine, using trial and error to refine it is perfectly fine with me. So if I was off by one, because I tried to write AA, but I got AB. And it's true for each one. So I just subtract one. This means I'm in control. I'm just off by a little bit. So I just put the -1 in and see if that works. And in fact, that does work. This is F3. Now I get AA, BB, CC, DD. So this, now I can print anything I want there. So now I'm ready to take over the box. I have a few other preliminaries to do, but now I can write an arbitrary word there. So, all right. I'd like to get this thing off my screen, see if I can do that. That should do it. There it does. All right, so, all right, that's what does it. Okay, now, I can write the chosen value in 4 bytes. Now, the next thing I can do is I can insert dummy shellcode. This is what the order I recommend doing it in. Because now I have figured out how to write an arbitrary value. The next question is the stack executable? It might not be, in which case I'm going to have to use a more advanced exploit. So the first thing I always try is CC, because CC is a break, but it has to execute to do the break. So I'm going to put in 100 bytes of 90 for not and 250 bytes of CC for dummy shellcode. That's F8 here. So let's see. I think it's F4 in my demo, F5. Let's take a look and see how F5 looks. I think that's it. And down here I got, yeah, that's it. So I put in 100 bytes of NOP sled and 250 bytes of dummy shellcode. So let's take a look at what this does. Now what I've done is, after I do all the printing that overwrites the pointer, I just put the rest of the stuff on this print statement, because that's going to be on the stack somewhere. And I'm just trying to get it in the machine somewhere. Then I'm going to find it and jump to it. So that's the game. And let's see if it works. This is F5. So if I run F5 here and start it from the beginning, I hit the breakpoint. Now, if I look at that address, it's, oh, here I actually targeted this number, BFFFF110. It could have been, but now let's just look at the stack. If I do info registers, we've been here before when we were doing stack buffer overflows. The ESP is here and the EBP is there. I just want to look at the stack. So let's do 40X ESP and see what's in there. SP and dollars, here dollars, there we are. Okay, so it is in there. Here's the earlier stuff. Here's my NOP sled, 9090. There's my CCs. So the stack, it's, you know, maybe 50 or 60 bytes down the stack starts my attack. This is all the junk I had to put in there to overwrite the return pointer. So I just need to hit somewhere in the NOP sled. And as you can see, this value will do it, BFFF110. So that's why I put it here, BFFF110. That's what I want to write in the pointer. So now I've done that. And remember, we looked at it here. That is actually the value here. So if I continue, it should hit exit and jump up to FY110 and then slide down the NOP sled and then hit the break here. So let's just continue. And you see it works. It hit the breakpoint trap and it hit it at BFFF F155. And that is right where it started. This is 055 is here. It hit it at 54, broke, and the next pointer is 55. So it works. This means I found the NOP sled, I can target the NOP sled, and the code is executable on the stack. And that's because of the note I made at the start in compiling it. I chose to compile it with an executable stack. If you didn't put that switch in, it would have stopped as soon as you hit the first 90 and refused to run, saying violation of permission. You're not allowed to execute the stack. And then you'd have to use a more advanced technique, return-oriented programming, for the whole exploit, which would be another whole lesson. So now that's the game. Now all I have to do is replace that with real shellcode, and I own the box. And that is something we've done before. We go to my slides. So there's the stack, there's the NOP sled, and there's the chicken address and the NOP sled to go to. Now you get a trace breakpoint trap, meaning it was able to execute it and hit the dummy sled. So now all you have to do is get rid of the bad characters and make shellcode. So I took the shellcode, which was, I think, 250 bytes of CC, and I just put in all 256, starting at 1, because I know 0 is going to break the string. So I know 0 is bad. And if I start printing at 1, what happens is I get the 0, 1, and then the 2 through 5, and the 6 through 8, but then it stops. So 9 is a bad character. I don't know what 9 is. I don't think it's a tab, but anyway, 9 is some kind of ASCII control character that is interpreted as the end of a format string. Remember, what I'm doing is feeding all this junk into a C format string, and I don't really know what the syntax rules are for C format strings. So that's why you just try characters and see what bad characters are. Whatever ASCII 9 is, it's bad. So now start at 10 and try all the rest, and you will see that here's the NOP sled, and I don't even get 1 byte of shellcode. It's just all zeros. So the 10 is bad also. The 10 terminates the input and nothing beyond it gets printed. So that's no good. So now I start at 11. And when I start at 11, I get 0B is 11. Then I get 0C, 0D, and on it goes until it gets to 1F. And then I don't get anything after 1F. It's all 0. Because 20 is space. 20 is hex is 32. So 20 is bad, which is not too surprising. The space breaks the format string. So that's it. Then I start at 33, and I find that it all goes in. I start at 21, which is 33 in base 10, and you see 21, 31, 41, 51, 61, right down to F1, right down to FF. All the remaining characters go in without breaking anything. So now I have found all the bad characters, which is 0, 9, A, and 20. So now I know how to make shellcode. We've been here before. You just use MSF Venom. You choose your attack. Once again, I'm choosing the simplest attack that will just listen on port 4444, just so I don't have to bother with details. I put in the -B to dodge those characters. When I did it before, I had trouble that my shellcode would run, and then when you connect, it would hang up on you. So I just looked for the advanced options for this attack, and there are some options about how to fork. And it turns out that prepend fork equals true is what prevents that. I don't really understand why, but I've analyzed a couple of these before, and I think I mentioned before, Metasploit payloads tend to be rude and write memory outside where they should write memory. So this option causes it to not crash when you connect to it. Something about the network connection uses memory that Metasploit payload overwrites. And I've spent like a week figuring it out, but now I've taken, again, the trial and error option. When I'm close and things are working, I just look for the options and try options until it works. And then, of course, I want it in Python. So that's the whole command that generates the shellcode. And when you get it, you just get a bunch of hexadecimal. So now you put in the NOP sled like before. You put in your shellcode, then you create padding because you want to keep the total length of it the same. If you forget to keep the total length the same, then what happens is the stack frame changes size. See, the way routines work, when you jump into a routine, it then reserves space on the stack for local variables. So it looks at how big the stuff you're printing is and determines how big to make it. And if you have an injection that's 100 plus 250, and then you make it 100 plus 100, it'll make the stack smaller, and now your location of everything is wrong. So the way to avoid headaches is to always keep the total size of what you inject the same. So I originally put in 250 cc's here, so now I take 250 minus length of buffer of padding and put it at the end, so the total size of it is the same. But then everything will stay in the same place as I exploited. And that's the attack that will take over the box. So let's take a look at that one live. But the last few steps there are nothing new, really. And that, I think, is what I called F7. That has the 4 bytes I write to. Here's the address I put in. Oh, yeah, this one here is kind of more cool. Let me go back to F6. There is, of course, one more irritation. Okay, this is the one, BFFF110 that we did before. So it injects that address into the exit pointer. And down here, it has 100 bytes of NOP sled and the buffer here and enough A's to make the total 250. And then I print out all that junk. The 4 pieces of format, the 4 pointers to format locations, the format string with the % ends in it, then the NOP sled, the buffer, and the padding. And this stuff will all end up down the stack about 50 or 60 bytes down because it's after all that junk goes on the stack. So let's run this one, that is F6, and see how it looks. So I run F6, and it's going to run and hit my breakpoint. Now I take a look at the stack. So here's the junk that readjusted the pointer. Here's my NOP sled. Here's my shellcode. And when the shellcode's over, I have all those A's. So now I have to jump back to someplace in the NOP sled, and I chose to jump here at 110. And you can tell that because if you look at that location, which is here, that's where it is. BFFF F110, that takes you back to here. So if I continue, it'll jump here, jump there, and run this shellcode. So if I do that, that's what it does. It exits normally without crashing. And if I quit and run netstat minus pant, now it's listening on 4444. And it is the FS process that's listening. It took over the process. Instead of exiting to quit, it then ran the shellcode and quit running and kept running. So now this machine is available to be taken over. So it looks great. Everything's fine, but we're going to get hosed. Let me try it outside GDB. So I have to free that port. Let's kill that process, 2120. And now if I do netstat minus pant, 4444 is no longer in use. So now I can try it out here. That was F7. I think it was F6. It was F6. Okay. So if I run FS out here with F6, it runs. And now if I sniff, it's on 4444. Well, okay, here's something to tell you. It worked. But when I did it this morning on this machine, it didn't work. So there are some uncontrolled variables. When I did it this morning, this crashed with this egg fault because GDB was off, and I had to modify it by just changing the value. So on the same machine, which hasn't even been restarted, I got a different answer. And that's why I had to change this to 40. So there are some flies in the ointment. And if you wanted to get to the bottom to it, you could be printing out values with this and watching how it changes. In fact, let me try one thing that should be kind of fun. If I do this, FS, just a %x dot %x, this should be kind of fun. If I do that, and then I do it again, I do not have address space layout randomization on, so I get the same answer every time. If I go into GDB of FS, and I do that same thing, which is going to be this, it's going to be run without the dot. There. It's the same every time, but it's off. This is 857 and this is 833. That's what I mean. This is why your exploits fail so much. It's different. The memory layout inside the debugger is close to the memory layout of the real operating system, but it is not the same. And you can see it. Here it is off by 33 to 27. That's 25 hex. I've seen it off by as much as 60. And sometimes it's higher, sometimes it's lower. It can drive you nuts. So when something works in the debugger and it fails outside the debugger, just try moving the pointer around. Of course, another cure would be to always use a nice big NOP sled like 300 and go for the middle. And then even if you're off by 100, it won't matter. Yeah. Well, because some of them are affected by the change in the environment variables. What people have told me is this all comes from the environment variables. If you're running out here, you are logged in as a user and there are environment variables and the program runs with a certain path. And if you run in here, it has different environment variables and it runs without all the preface in the path. So the total length of the first command line is different. And that causes certain things to be relocated, but other things like library routines are not relocated. So some of the objects on the stack are in a different position and some of them are in the same position. That's why there are some, I've even read some blogs where people try to adjust all the variables to make these things more similar. But in my experience, there is nothing easy you can do that makes it 100% right. And I've just gotten used to the fact that, like every other hacking tool, it's a little messed up. And it's pretty close, but GDB is not exactly the same as being out of GDB, and you just adapt to that. And that's why you always use an op sled in addition to other things. So be aware, yours might not work outside the debugger. But and I've never found a pattern. And this is like the worst case I've ever seen, where the same code in the same machine is now off by a different amount it was this morning. That's rude. Seriously rude. But that's life. Now I'm happy to do it at all. So anyway, that is the format strings, and you have a project here to do it. And it works on Kali 2017.3 and Kali 28.1. So I think I may have finally gotten to the bottom of the latest versions of Kali. For the last couple of years, they've been driving me nuts by turning on more and more protections by default in GCC. And it took me a couple of years to learn how to turn them off again without going nuts to make any of this stuff work. And we are slowly moving towards modern exploits. The format string exploit is an old one, but it will just keep happening until people learn to scan for it. It's still not included by default in the debugger. Anyway, I think that's all I wanted to tell you. Are there any questions about anything? Saw a few things come in the chat. Here's another one. Man ASCII. Yeah, that's right. I'd like to know where I can download the source files. Yes, if you want to get anything I'm using, you can't download the Python, but what you can do is just copy and paste it. If you just go to samsclass.info and 127 and projects, and then go to project 6, it's all here, and you can just copy and paste from here to get the source code. I didn't make it downloadable, but that amounts to essentially the same thing. So all the commands you can just copy and paste here into your Linux machine and go through it all. Any other questions? Well, I think that's it. I'm going to stop the Zoom, and I'll go up to the lab and help anybody who wants to work here. Another question's coming in. Thank you. Okay, great. Okay. I guess I'll hear from you guys next week. Yeah, print. Here's another Python trick to print a character $41. Sure. There's a lot of ways to do it. All right. I'm stopping the share, and that's it till next week. Good.